Guys, we're going to continue on with iron it out number 4. And in the previous video, we did determine that this charge of iron is going to be iron plus 3 because we compared actual mole-to-mole ratios from a balanced chemical equation to an experimental set of mole-to-mole ratios. Was it perfect? No, but it was pretty close. So I am going to rewrite this balanced chemical equation at the top on number 4. So I'm going to do that right now, and you guys can do that as well. So we know this was Fe plus 3. So that was our 2 moles of iron solid reacting with 3 moles of cobalt to acetate. 2, write this, yielding 2 moles of FeC2H3O2 in solution and 3 moles of cobalt solid. Okay, so I've got my balanced chemical equation from the front. Now I can answer some questions. Which of the reactants is the limiting reactant? Offer proof. And again, reagent's another great word. I usually say reactant. Either one's okay. All right, so you guys could go through the process of a BCA table and you could find the limiting reactant that way. But remember, when you have an actual experiment, it's super easy to find the limiting reactant and the excess reactant. The limiting reactant is the reactant that's used up completely. There's none of it left over. The excess reactant, you can always see and hold in your hand after the reaction goes to completion. In this case, that was the discussion about the iron nail. Only 20.94 grams of iron was left over, meaning only 0.60 grams of iron was used up. So I am confident that the limiting reactant is the cobalt-2 acetate because there are 20.94 grams of iron. The other reactant, excess reactant, is left over. It's super easy to find limiting and excess reactants when you have a lab situation because you just have to really read that lab situation carefully. One reactant's left over, the other has to be the limiting reactant. All right, how much cobalt should have been recovered? This is theoretical when perfect on paper is done. On the previous side, we have the experimental grams of cobalt, but we don't know, on the front, we have the actual grams of cobalt from an actual experiment. So we want to know theoretically how many grams of cobalt should be recovered. So when it says how much, we're actually going to go to grams because yields we are going to express in grams. Don't just stop at moles. All right, so to start this problem, we already know the limiting reactant. So we want to start with the limiting reactant and then determine how much cobalt. We don't want to use any of the iron information because the iron wasn't completely used up. When you do a problem and you know the limiting reactant, we're going to start with the moles of limiting reactant because it all gets used up. The reason I'm starting at moles is because I know the moles from the previous page. I know the moles of my limiting reactant. And I'm going to use that because I can skip the BCA table. I've already determined the limiting reactant. I'm going to go from moles of my limiting reactant, which is cobalt C2H3O2, and I am going to go to moles of my product, cobalt. How much cobalt should have been recovered? So I'm going to have to use a mole-to-mole ratio here. And once I know my moles of cobalt, I'll be able to calculate my grams of cobalt. and I will then know my theoretical yield. Perfect on paper. And again, if you know the limiting reactant, you don't have to do the BCA table to do your mole to mole ratio. You can just start with your limiting reactant, use that all up theoretically to make your moles of cobalt to grams of cobalt. Then once you have that step, you can do your percent yield. And remember, your percent yield is actual yield over theoretical yield. Don't forget your units of grams here, folks. And then we're going to multiply by 100 to get our percent yield. And then we want the mass of iron. Ooh, now we know that it's iron 3 acetate was produced. Or theoretically, how much could be produced? This is another practice problem for you. We need to take our moles of limiting reactant. You remember what that is? Then we need to go to moles, this time, of a substance we haven't really used much before, the iron 2 acetate in terms of grams. So if all the moles of limiting reactant are used up, how many moles of iron 3 acetate can we make? Oh, sorry, this is supposed to be 3 the whole time. Let's fix it right now. Because the whole point of the front was to, I apologize, folks, make the Fe plus 3. I wrote the wrong one down. 3. Did I do that on the front too? 2 Fe, 3 cobalt, 2 Fe. I forgot that little 3. Little numbers are important in chemistry. All right, much better. Iron 3 acetate, because acetate's not good at 1. There we go. Okay, and remember our yields are always in grams, our theoretical yield. So we'll have to go from then our moles of Fe, C2, H3, O2, 3 to grams of the Fe. Can I fit it in here? C2, H3, O2, 3. Okay. Then the big question, summarize the process of how you determine the charge was iron plus 2 or 3. You need to talk about how you knew that this was an Fe plus 3. What did you do? Think back. First, you looked at actual mole to mole ratios. Then you were given data in grams from an experiment. You took experimental grams to moles. Then you compared experimental mole to mole ratios to actual mole to mole ratios. Your challenge is, can you summarize that? Maybe you can write some step-by-step ideas of how you did this. And then I know I haven't given you any answers for 5 or 6. We'll come back. We'll talk about these in class. We'll check the key and we'll answer questions together. Good luck, students.